Welcome to the Chapter 7 Guided Practice. In this notebook, we will connect several concepts we have already used, NumPy, Panda, Matplotlib, and scikit-learn, to build a binary classification model. We will begin with the sigmod function, visualize how it works, explore the breast cancer dataset, and then train a logistic regression model. At the end, we will evaluate the model using accuracy and confusion matrix and a classification report. One important detail before we begin. In this dataset, 0 represents malignant and 1 represents benign. Okay? So first we import the libraries and tools we need. So let's do NumPy. Remember, handle numerical arrays and calculations. Let's do pandas. That will help us organize results in tables. Matplotlib, pyplot. Let's see. Yes, looks fine. That will create our visualization pretty much. So let's also head through here some extra elements that we will require later. So let's do from scikit-learn. Let load the let breast cancer. Let's import logistic regression. You know what? Let me just copy and paste. It probably will be a lot better and minimize my typos there. Let's import model selection train test split or standard color. And from metrics, we need to import a couple of elements: accuracy score, confusion matrix display, and classification report. So that way we just pretty much importing a bunch of elements. And let's import also display so we can utilize it. And let's just print some configuration. Easy to read, just to be able to see it with the precision at 4, so it doesn't have that bunch of numbers and zeros at the end. And we will print libraries just to see if this actually works. Let's try it. I know that before we just using imports all over the place. In reality, it's a best practice to keep the imports together at the beginning to make the notebook easier to read and ensure that all required tools are available. We see our printing is actually working. That means that we can proceed. So we need to define our sigma function here. The sigma function converts any real number into a value between 0 and 1. This is useful because logistic regression needs a probability. The formula is 1 divided by 1 plus a raised to the negative x. In Python, we can use NumPy. Allows this function to work with either one number or an entire array. We test with -2, 0, and +2. So let me show you that. So we just need to define sigmoid x and return 1. Oh, sorry. Define. I'm telling you, I cannot do several things at the same time. 1 plus NumPy, the exponent, would be O minus x, right? So a quick evaluation that we can use here. Let's put it as a quick check. Of string representative values. So let's do example values. Let's do a simple MP array. Let's do -2, 0, and 2. And let's just print the values and the sigmoid for those example values. So example values MP array, I have an issue here. What is having the issue? I'm actually not sure about it. Oh, array, I missed an error. R over there. Cool. So we can see that -2 produces a value close to 0. 0 produces exactly 0.5, and 2 produces a value close to 1. So that's pretty much what it does. It gives us that complicated, like the lower one is going near 0, and the biggest one will be almost 1. But you can see the 0 is actually exactly in the middle between -2 and 2. That way give you the dot 35. So that we can usually the sigma function. So let's do the discrete values. So we create an integer values here. Let's do x equal MP array -10 and 11. And let's do the sigma of x using assign it to y. So we pass the entire array to a sigma function. And let's put those into pandas data frame. So let's create a table. We send x to x, and sigma x will be y in this case. And we just display that one. That will be a pretty cool way to show it. And we just have those right there in order to be printed. These midpoints will later help a model to decide between two different cuts. This table makes the pattern clear. A large negative input approach to 0, and a large positive input approach to 1, but 0 itself approach to exactly in the middle. This will be later helping them decide those two classes itself. So let's do, to create a smooth graph, we usually generate values using the smaller step of 0.1. The curve has an S shape. The dashed horizontal line marks the probability. And let me just showcase that. That will be nearly. So let's do very similar what we did before. X smooth will be -10 to 10.01. Remember, this is exclusive. And we define the step. So we have a bunch of more numbers there. So let's do the sigma now. And the idea, let's just plot it out. And I will just copy and paste a bunch of stuff right here. And you can see those. You can pause the video if you need to. So we just create a fixed size 8 to 5. Plot, we just plot x, y. We have a line and we just put the label x line right there. So when we execute this, we can see that sigma and that S shape that was mentioned before. So this dash over here marks the probability of 0.5 exactly. So it goes to the 0. Values below this point can assign to one class. One values above, it can assign to other class. So the sigma function does not directly know what malignant opening means. It only converts a model score into probability. That's what it does. So now let's load scikit-learn build breast cancer dataset. Right? So let's load it. with the load breadth concept, we re-important the top. Contains with, right, if I remember correctly, 516 something, 69 maybe, samples of numerical features. To two possibility values, 0 for malignant and 1 for benignant. For visualization, we use a mean radius and a mean texture. Each point represents one tumor sample. So let's do features 1 and 2, mean radius, mean texture, and their target will be cancer target. And let's plot it out. So we can actually see those. So we do for class value, we just enumerate the cancer target names. We just mask those out so we can actually print them. And let's see it. Like you can see right there, those. So we can see some, for the evaluation, we use the mean radius and the mean texture, right? We can see some separation between the groups, but there is also an overlap. So mostly the malignant are here, the benignant is over here, but we can see those overlap happening in this area. So we can see the sample, we have 569, we have 30 features, and the target names are malignant and benign. So we can see those through there. So let's do the 3D visualization. It will add a perimeter as a third feature. So let's have those one. So let's first get from a cancer data. There you go. That's perimeter. And if you can print the whole cancer data itself, you will see all the different features. But let's select the column. Let's do the figure for the plot side and let's put it there as a 3D view itself. We just change here projection to 3D. And let's print almost the same, adding the C label now for the 3D part. And this will help us understand the relationship between there's difficult to notice in a flat graph. Radius and mean perimeters are related, and the malignant and benign samples from visible regions now. Visualization helps us understand the data, but the machine learning model will perform the actual classification. So we can see those through there. Oh. So let's examine the mean radius by itself. Before using all 3 features that we need, we will build a simple model using only mean radius. The y-axis will show the class, malignant at 0 and beginning at 1. So let's get that small amount. So let's do a specific value. Let me show you. So let's put this here. So this will generate a random number with the seed is 42, right? And we are telling it that this mean of the random number will be 0. So we'll put numbers on top of that. I'm setting the deviation. The standard deviation is 0.025. I know that probably talking complex math. Don't worry about it. This is we just will add those to our size, the target size. So we have that separation. So if we have target like 0011, it would do something like minus 0.01 with 0.02. Everything that goes to 0, it would be a little bit different, more or less. And the next one that is actually 1 would be a little more different. That will help us visualize the jitter target. So let's add like a change on the sizing so we can see those data. So we'll do the separation because without the overlap itself, this will help us understand those a little bit better. So let's now pretty much put my code for the graph itself, and I'm doing the plot for that jitter one. As you can see there that now we're able to see in this scatter plot. And we can see where they have that overlapping, but Now we can able to see those scattered a little bit better. So we can just verify the information. The smaller radius values are normal, commonly benign, and while larger radius values are normally malignant in this specific dataset. So let's train one feature logistic regression model, right? So for that, we reshape the mean radius into two-dimensional feature matrix because it can expect rows and columns, even when there's only one feature. So let's put those there, right? Let me just play it. Then after we did that, we just create the logistic regression on the model and fit it using the mean radius and the non-target label that we have right here, right? The coefficient is negative, and it tells us that the prediction probability of an ink generally decrease as the mean radius increase, more or less. So the model approximately 50% decision point is a mean radius of 1476. Using only this one feature, the model reaches about 80% more likely it will 8.87, right? Accuracy for the full data set itself. So the decision point is 1476. Training accuracy is only mean radius is 87%. I can see that. So let's visualize the logistic regression probability here. And this has a little more lines so you can see those. You can pause the video anytime you need to type those out. I just don't want to make this video really, really long. Yeah. So oops, there you go. The point are the actual class label, and the curve is well predicted with the sample as benign. There you go. The smaller radius values, the probability is benign is high. As radius increase, the probability falls. We can see those through here, right? The horizontal line marks the exactly the middle, 0.5, and the vertical line marks the approximately decision radius that we have through here. This graph shows how logistic regression uses the sigmoid shape to move smoothly from one class probability to the other, pretty much. Let's compare probabilities and final prediction for now. Let me just copy the text. We'll paste those there. So predict proba, in this case, give the probability for both classes. Each row adds up to 1 that we have right here. For example, a mean radius of 10 receives a very high probability. A benign, a radius of 20 receives a very high probability of malignant. Predict converts those probabilities into final class. By default, the class with the higher probability is selected. The probability gives us more information than the class label alone because it shows the model confidence here. As we can see right there, with different probabilities. So 10 is given more. 20, 25 is still the malignant in this particular case. So let's train a complete model with all the features itself. This will be really interesting. So actually, I'm jumping through here. We can see there, the biggest value is the one that is assigned the prediction that we needed, right? Let's do the test split now. And let's get X to be the whole data, no specific ones, and Y the whole target. And let's do the test split. Let's do a test size of 80/20, right? So let's do test size will be 20, 80% will be used for training in this particular case. And let's do a standard scalar to do the training data set itself. Oh. So we create a stronger model using all those features itself. We split data set in testing set. As I mentioned before, 80 go to the training and the test site will be 20. The random state make the split reproducible. So we receive the same results each time. Stratify kept the class proportion similar in both sets. We then standardize the features, and that's what it is really important. This matters because measurements such as area, radius, and smoothness use different scales, so the scalar is fitted only on the training data to avoid allowing information from the test set to influence training. Finally, we train the register regression with a larger max tier, either, and so the optimization has enough interaction to coverage. So we have training for 55 is what it was trained. Testing was 114 rows, and we can see the accuracy was around 98%, and the test accuracy was 98%. So the test accuracy here is more meaningful result because it measures performance on data the model did not see during training. So this doesn't, it is important, but it's not that much. But this is the important one where we can actually see that is 98%. So it did a really good job in training that information. Let's do the intercept now. Let's review the model coefficient. Let me put all the code there. And we can explain it. So what has one intercept, one coefficient for each of the three features here. Because we standardize the features, their coefficient sizes are easier to compare. A positive coefficient pushes the prediction toward benign, which is a class 1, and a negative coefficient pushes the prediction toward malignant, which is a class 0. The table sort features by the absolute size of the coefficients. This helps us use to see which features have stronger effects in this particular model. A large coefficient does not automatically prove that a feature causes the diagnosis. It only describes how the trained model uses that particular feature. Let's inspect test prediction then. So we need to train the linear regression using all the features. We already did it. So with predicted probabilities, extract the predicted one, and compare those predictions for actual results. And we are right here. So here we predict both probabilities and the final class for the test set. The table compares each actual class with the model. Prediction includes a Boolean column showing whenever the prediction was correct. In this case, the model correctly predicts 112 or 114 test samples. We can see those through here, right? With only 2 incorrect predictions, that gives us accuracy that over 98%. And it's a really good one for this particular case. So let's see the confusion matrix evaluation of the problem. The confusion matrix tells us what type of prediction were correct or incorrect. Routes represent the actual classes. and columns represent the prediction classes. The diagonal contains correct predictions, while the up diagonal contains mistakes. The model correctly identifies a specific group. So let's see those right now. We do the confusion matrix that we imported with our testing and our prediction. Let's do our data frame table. And let's display that with those particular values. You can see the confusion right here. So the model correctly identifies 41 malignant samples and 71 benign samples. So these are the correct ones. Actual malignant and predicts malignant, and actual benign and predicted benign. It predicts one malignant sample as benign and one benign as malignant in this case. So accuracy tells us the number of correct, but the confusion matrix shows exactly where those errors actually happen. So we have here in this case the false predictions in those two. So these are the true predictions, and this one are the false prediction. So let's do the classification report. Actually, before the classification report, let's show it, visualize that confusion matrix. So we can see it through here, but we can see more in the plot side. So that one should be. What is important shows well the model does. And we can see the number, like the stronger the color in this case is how much it had it. And we can see right there the confusion metric, the same values. Those are the positive predictions, and those are the negative or the false ones. So those are the true ones and the false. In this case, this is a true malignant. This is a true benignant, false malignant, false benignant. So that's pretty much what it is. It's a in the prediction percent. So here, remember, the data set that it has is just 1 as for benignant, as 0 for malignant. So this is the positive side to keep it away. But remember, usually what they do is just change those in order, because you don't want to predict something benignant. You actually need to predict the malignant part. This is what we discussed in the video lesson, right? So they can change those. True, but in this case, let's keep it as it is. So we eliminate that complexity. So this is a true positive, true negative, a false negative, a true positive, a false positive, and a true positive. In this particular case, that's how that actually works. Wow. So let's summarize several evaluation metrics here with the classification report. Copy this, let me paste those. Cool. So our classification report that we imported, the test target malignant 0, benignant 1, and digit 4. And we have it through here. Precision tells us how often a prediction for a class was correct. Recall tells us how many actual members of a class the model found. F1 score balances precision and recall. Support is the number of test samples in each class. So we can see those through there. Both classes have precision, recall, and F1 scores about 97%. In this test split, the overall accuracy is approximately around 98% that we can see it through here. These results are strong for this guided exercise. But remember, this is educational demonstration. A real medical system would require much more validation, oversight, and testing. This is just for education purposes. Don't use it to make a real medical decision. That's not what it is for. So to summarize, the sigmoid function converts a numerical score into probability. Logistic regression uses that probability for binary classification. We first use mean radius alone to understand the model visibility. Then we use altered features, separated training data from test data, standardize the features, and evaluated the final model. The main lesson in this building, a model is only one part of the machine learning. We must also understand the data, prevent data leakage, test on unseen examples, and examine the kinds of mistakes the model makes. So remember, as always, print it out as a PDF and upload it for the class right now. Now, I've been seeing a lot of those PDF being cutted, like sometimes does cut uh, and it doesn't show everything. If that happened to you, send me a screenshot of the missing part. So you can upload multiple files actually. So you can do that. So that way you will have a full credit. So let me try to print this. Let me see how it looks like. So far, looks like it get cut at the end. This usually take as a good one, but if it's actually cut longer, like actually shorter, yes, you'll send me a screenshot of the missing part itself. I've been told also that sometimes this happen. Don't worry about it. You can use that. But there is also no resource that one of the students actually showed me that I like it. So let me just save this and let me see if I can actually download, um, save a copy in Drive. Let me go back to my Drive and I should have somewhere my copy. So this was the file. Let me see. Um, it didn't save it through here. Oh yeah, Collab Notebooks. So we have that copy of chapter 7. Cool. Let's download this. And I think he showed me was um, Jupytools, something like that. No, let me verify really well. It's not this. Let me check in a minute. Okay, I found it. It's jupytools.com. So let me just upload the one that I solved it. So it should be converted somewhere there. Let's do PDF document. Let's try that. And we should be able to open it in a way. No, I didn't do the way that I needed. Probably let's try the Word document. So some of those actually works and looks pretty cool. I don't know which one he used. So oops, reload, convert and export. Let's do the kernel unknown, view notebook. Yeah, we can see it right there, including the graph and everything that we just did. And I think we can accept this and probably we need to do the HTML document. Yeah, that actually works in a way. But we give you this with some kind of um, content thingy, but then you can see it's a lot better organized. That way it has everything there. And if we print this to PDF or save it as PDF, it's a lot better. It has everything that we need. Now, the exporting to PDF itself should actually work, but somehow it didn't do it correctly. So this is not mandatory. I want to be really sincere, completely sincere there. Let me try the PDF one more time. Yeah, no, he's not doing it. Probably the image. Now I'm just playing around. No, sorry for that. But yeah, um, you can pretty much download it and use the one that you want. Uh, the Word document should work actually. I don't know why it didn't. There's an issue there. And import it like that if you want it. If not, the old way just to printing through here should work with an extra screenshot of the missing part. Like for example, this just send me a screenshot of the last part and should be more than enough. So I really hope that you like it. As always, any question or doubt, don't hesitate to reach me. Happy coding, everybody.